In this slide, we will be learning about the inverse of a matrix, and actually we can use the LU decomposition for taking the inverse of a matrix. That's why we will be studying inverse first, then talk about the LU decomposition for inverse. So if a matrix A is square, then there is an inverse of A defined as A minus 1. So this is for square matrices only. And A times A minus 1 is equivalent to identity matrix actually. And the inverse can be computed in a column by column fashion by generating solutions with unit vectors as the right hand side constants. What it means is that basically we will have a matrix, for instance a 3 by 3 matrix, and let's write it here maybe A11, A21, A2, A31, A12, A22, A32, A13, A23, and A33. So this is our matrix, for instance. And we want to take the inverse of this. And also we have x1, x2, and x3. This is the general equation, let's say b1, b2, b3. So, but taking the inverse of a matrix it is not necessary to use this just for this. What we need to do is, for a 3 by 3 matrix, if you want to find the first row of the A matrix inverse, then replace the first row of A matrix by a B matrix of 1, 0, 0. So simply just remove these and put these here, then solve. So if the right hand side constant has a 1 in the first position and zeros as well, this one, the resulting solution will be the first column of the inverse matrix. Then for the second column, we will apply the same for the second row, second column. So we will remove these, but this time the second row will have 1, and we will put these here. And this actually explains that if right hand side has a 1 in the second position and zeros as well, this one, the result will be the second column of the matrix inverse. So by solving this with this inside here, then it will give us the second column of the inverse of the matrix. We will do the same for the third one by implementing 0, 0, 1 and putting it here. So, and the best way of having this implementation is actually LU decomposition, and we will show this in an example, and then you will understand how this inverse can be obtained using the LU decomposition. We have an example here, example 10.3, to use the LU decomposition for taking the matrix inverse, and this is the example, which is the A matrix from example 10.1 and 10.2, of course. And in 10.1 we already decomposed this into L and U, and you will do the same for finding matrix inverse as well. Just decompose the A matrix to L and U, and these were the matrices that we found. Now we just need to use the forward substitution step. How are we going to use that? Let's write here first. First, for the first column. For the first column, use forward substitution with a unit vector. And in this unit vector, we will say B, only the first row will have 1, the rest will be 0. So we will just use as the B. Then we solve by this, the L D equals B. Simply in the forward substitution, if we write this in detail, it will become, so L matrix is 1, 0.033333, 0.1, 0.1, minus 0.02713000001. This is L matrix. And for the D's, we don't know these. D1, D2, D3. And B is 100, not the solution matrix. It's just 100. So let's solve for this. For the first term, D1 becomes 1. You can see. For the second term, 0.033333 times D1, which is 1, plus 1 times D2 is equivalent to 0. Then D2 is minus 0.0333333. And from the third one, 0.1 times D1, which is 1, minus 0.02713 times D2, plus 1 times D3 is equivalent to 0. Then D3 is minus 0.1009. So these are the results of these. And this is the first row of the matrix inverse. So maybe we can write the matrix inverse somewhere. Actually, no, this is just the D values. Then we use the back substitution as the right hand side. Now use back substitution with this. Then we will get the matrix inverse, which means U times X minus D actually equals D. We will solve this. In here, the U matrix is, sorry, let's write it in black. Actually with this 3, 3, 0, 0, the U matrix from here, minus 0.1, 7.00333, and 0, minus 0.2, minus 0.293333, and 10.0120. This is U times, we don't know X's. And these X's actually the first row, first column of the inverse matrix. And these are 1, minus 0.033333, and minus 0.1009. Let's solve this. If we solve this from back substitution, from here, x3 becomes minus 0.01008. I will not write the details, but from here, if we put x3, only x2 will be available. Then x2 is minus 0.03333, and from here then, let's move like this, back substitution, x1 becomes 1. No, actually these are not correct. The results are minus 0.00517 and 0.32249. You can see this is the first row of A inverse of the A. Okay, we obtained this. Now we will do the same as the second step for the second column. Let's do it in the next slide. We will basically implement this again, but this time this will be 0, 1, 0. Let's work on the next slide. For the second column, B's are, now the second row will be 1, 0, 1, 0, and use it in the forward substitution. In other words, L D equals B, and solve this. And B is 0, 1, 0 actually. Let's make this B like this. So if we write again the L matrix 1, 0.03333, 0.1, 0, 1 minus 0.02713, 0, 0, 1. And D1, D2, D3 are unknown. And the B matrix is 0, 1, 0. Then from the first row, you can see there is only D1, which is 0. Then from the second row, D2 is equivalent to 0.03 times D1, which is 0. Then D2 is 1. And then from D3, here, you can see, so this is 0, this is eliminated. This is 1 times D2 and D3 equals 0. Then D3 becomes this value, 0.02713. Then use this in the back substitution. These substitution, and in this we have u times x's equivalent to these d's. If you solve this, let's write the u matrix. Three, 0, 0, minus 0.1, 7.00333, 0, 0.2 minus 0.293333, and 10, 0, 1, 2, 0. And these are 0, 1, 0.02713 equals, actually these are x's, sorry. These will be on the other side. x1, x2, x3, and these are 0, 1, 0.02713. So from back substitution, you can see, let's start from here. x3 is simply 0.00271. Actually, there's a, oh, sorry, we divided by 10. Then move it to the top. From here, x2 is 0.142903. You can do the calculations. And from the first equation, x1 is equivalent to 0.004944. Okay, these are the second row or second column. Second column of a-1. So when we used 1, 0, 0, applied forward substitution, back substitution, we obtained the first column of a-1. Now here we use 0, 1, 0 for forward substitution and then back substitution. Then we obtain second column. Similarly, we will use the third ones for the third column. B's are 0, 0, 1. The third row is 1 now. Then forward substitution using L, D is equivalent to actually B, let's say B3 to this. This is B2. Maybe this is B2. This is B3. If we use the same, it is the same here. This is the same. This is the same. Only this one is changing. When we apply this, I will not write the details. From here, D1 is equivalent to so I will not write D either. Actually, we already find these D1, D2, D3. Basically, D1 becomes 0, D2 becomes 0 as well, and D3 is simply multiplication of this by this one, but this is 1 now. So in here it was D1, D2 equals 0. Now D2 is not 2 then. D1 is 0, D2 is 0. Yes, this should be 0. And D3 is 1 divided by minus 0.02713. So, and we are going to use this now for the back substitution. Back substitution of U times X equals D. And D is actually these values are here. If we solve this as well, from here we will find X values because we know U already here. So X1, X2, X3. So we will apply back substitution. That's why we start from back. And X3 becomes 0.09988. You can write the details. I will not write them. X2 is 0.004183. This is the same practice that we do here actually. Just change this by this one. And X1 is 0.006798. And this is the third column of A-1. Okay, then by using these, A-1 is equivalent to, so the first row we already found it in the previous slide. You can go there to remember. 33249 minus 0.00518 and minus 0.01008. So the second column is now these. From the second column calculations, sorry, not these ones. X1, X2, and X3. So 0.004944, 0.142903, and 0.00271. And the last one, this comes here. 0.006798, 0.004183, and 0.09988. You can see we obtained A-1. And you can validate this. Validate by, we know A matrix from beginning. We found A-1 here. If we multiply this, this will be an identity matrix. If you find an identity matrix, then your result is correct. So this is how we apply the LU decomposition to find an inverse of a matrix. You can use the same practice for different exercises as well. In this slide, we will answer the question of why we need the inverse of a matrix. And basically, the inverse of a matrix is useful to be able to make an error analysis and to find the system condition and evaluate the system of equations. And here also it says matrix inverse can be used to discern or differentiate whether systems are ill-conditioned or understand whether systems are ill-conditioned. So three methods are available for this purpose. First of all, we scale the matrix of coefficients, normalize them in other words, so that the largest element in each row is 1. In the first row, for example, the largest will be 1, the others will be less than 1. And invert the scaled matrix, and if there are elements of A-1 that are several orders of magnitude greater than 1, it is likely that the system is ill-conditioned. So first, have a normalized matrix of A. For each row, there will be the maximum constant will be 1. Then take the matrix of it, inverse of it. How? By using LU decomposition. You can get the inverse. Then check the coefficients, basically A terms, and if they are very big, very large, several orders of magnitude greater than 1, so for example 100, there is a 100 value, then that means the system is ill-conditioned. So if A minus 1 have small values, then the system is not ill-conditioned. This is the first method. The second method, multiply the inverse. Actually, you need to take the inverse first using LU decomposition again. Then multiply the inverse by the original coefficient matrix. So A times A minus 1. And assess whether the result is close to the identity matrix. If it is close to the identity matrix, then you are okay. If not, either you made some mistake during the taking the inverse, but let's say you didn't make any mistake, but still there is no identity matrix. Then it indicates that there is an ill-conditioning problem, because taking the inverse requires so much work, requires so much operations, and even though you make the correct operations, no mistakes, still you may not have the identity matrix. In that scenario, that means taking the inverse is not possible, and because the A matrix is already ill-conditioned in the first place. So this is the second method. The third method is invert the inverted matrix. We will take the inverse again by using LU decomposition, then invert it again. So normally we will be able to get A again. Assess whether the result is sufficiently close to the original matrix. So if we get A again, then that's okay. But if we are getting another matrix, different values, then it also indicates that the system is ill-conditioned. Basically, all have the same idea, especially the last two, because this is just multiply A by A minus 1. If it is not identity matrix, then there is a problem, ill-conditioning problem. Here also take the inverse again. If it is A, that's okay. If it is not, the system is ill-conditioned. The first one is a little bit different. It's just normalize and take the inverse and see if the values are very large. If they are very large, ill-conditioned. Not very large, then that's okay. So these are three separate methods. You can try, all of them together or separately, only one, to check if the system is ill-conditioned. Okay, these are very long though. Taking the inverse, evaluating it takes so much time. Instead of that, actually, researchers also proposed another way, a matrix condition number, which is simply the maximum absolute row summation norm. So it is defined as this. The norm sign is this for A matrix, and we simply sum or add all the terms in one row, then get the maximum of it, then get this norm value. So condition A is simply the multiplication of norm of the original matrix and inverse. So we will taking the inverse again, take the inverse but without normalization. Of course, for these, no need for normalization for these. But even if you made the normalization, still A times A minus 1 should be identity for this, for example. Here also, you can get just the summation of each term in one row. In the second row as well, get the maximum. Sum the values. For the third row, sum the values and get the maximum of them for A matrix as well as for A minus 1. So for this, apply LU decomposition, get A minus 1. Then sum each row terms and get the max. Multiply just these max values. It will give us a condition number. If this is very larger than 1, then the A system is ill-conditioned. So this is a fourth way, actually, maybe we can say. This is just the fourth method. Okay, with these, so it means that to be able to evaluate if A is ill-conditioned, we need to use the inverse of the matrix for all of these four. And don't forget to take the inverse, and it is very important to understand if the system is ill-conditioned, because if the system is ill-conditioned, then we are not able to solve it. This is the end of chapter 10. You can have more information about this by reading chapter 10 in your book, and the pages are here. And thank you very much for listening, and see you in the other class.